Last class we discussed about electrochemical series. So electrochemical series is nothing but there is arrangement of respect to electrode potential in the increasing order of their standard reduction potential. So based on that electrode potential based on electrochemical series, you can choose best oxidizing as well as reducing agent, right? So you can predict which type of reduction is feasible. So you can determine the electrode potential. So you can determine also which metal will displace respect to hydrogen gas with reaction with the respective acids in this case. So next part of this chapter is that is Nernst equation. So you can determine. So this gives this Nernst equation gives the relationship between, that is quantitative relationship between concentration of ions and electrode potential. So this gives a relationship between. So this gives the relation. This Nernst equation gives the relationship between concentration of ions as well as electrode potential. Means as the concentration of ion changes, the electrode potential of the respective component or element also changes in this case. So in general, that is the reaction. This one is reaction. So for this reaction, that electrode potential can be written as like this. This one is electrode potential of Mn into M, and it becomes E naught of Mn into M. It becomes RT by E and F. Ln of concentration of Mn plus and concentration of M in this case. Or the same equation can be written as E of Mn plus M and E naught of M by N, then plus minus of RT by NF. Ln of concentration of M divided by concentration of M. So this is about for this reaction. This is general reaction I am taking. So that is ion that will take the electron, formation of a metal in this case, or formation of an element. So for this reaction, the electrode potential as well as the concentration of ions can be related or can be obtained by the Nernst equation in this case. So this one is a Nernst equation. This one is the electrode potential of a particular element. This one is a standard electrode potential. This one is gas constant, temperature, and this one is number of electrons involved in the reaction. If you take for this reaction, there should be a n number of electrons, and it becomes Faraday's constant. F is nothing but Faraday's constant. Ln of concentration of M raised to n plus n. This square bracket is very important in this case. This will represent the concentration of a particular component. So this one is the concentration of a metal ion, and this one is the concentration of a metal. The same equation can be written by changing this factor by putting minus sign in this case. So therefore the same equation can be written as, here it becomes a minus, we need to change this one. Here this concentration of M divided by concentration of Mn plus. If you put the standard values, already you know the values of this one is a gas constant, that is nothing but 8.314. T is the temperature, so if you take a standard temperature 25 degrees Celsius or 298 Kelvin. F is 96,500, that is Faraday's constant, 96,500 coulomb per mole in this case, and the same as it is. So if you put the values now, so it becomes E Mn. This one is E naught of M and plus of, okay. So if you change this ln into log now, to the big step, 2.303, and R is nothing but 8.314, and temperature is 298, then it becomes, and as it is, and Faraday's constant 96,500 per coulomb, then as usual log of the same here, the concentration of Mn So if you calculate this one, finally you get this equation. E is equal to Mn by M. So this becomes E naught of Mn by M in this case. Then it becomes plus of 0.0591 divided by N times log of Mn plus and all this same equation can be written as E of Mn young in this case, E naught of and 0.0591 divided by N log of becomes concentration of oxidizer state divided by concentration of reduced state. Right? So this one is about equation. So already you know the gas. So you are transferring ln to log in this case. And therefore, whenever it is transferred to ln to log to the base 10, it should be multiplied with the 2.303. So 2.303. So R value is how much in this case? Gas constant 8.314 joules per Kelvin per mole. Temperature, standard temperature, that one is 25 or 298 Kelvin divided by n. So it should be unknown that for this reaction there should be n number of electrons. And F is current constant, that one is 96,500 coulomb per mole. So log of same thing, concentration of metal ion, that is concentration of metal. So if you calculate this whole term, it becomes 0.0591 divided by n, the same log of concentration of metal ion, then concentration of metal. So this one is oxidized state and this one is a reduced state here. Means here n number of electrons will be transferred to the metal, that becomes concentration of metal. So therefore this one is Nernst equation in general. This is general equation for a Nernst equation. Here you can determine this n by knowing the reaction. So here one of the electrode, for single electrode, the one of the electrode is standard hydrogen electrode. So already you know the reason, the electrode potential of standard hydrogen electrode is considered as 0. So therefore in this case, the one of the factor is 0. So other factor is nothing but the electrode potential of other electrode can be determined by using this equation. So this is about single electrode. So next time we will go further for two electrodes. For two electrodes, so for two electrodes, so for example, in general you can consider galvanism. In general, that is Zn2 plus copper 2 plus copper. So cell potential, this is E and E naught of copper 2 plus copper and E naught of Zn2 plus Zn. So this is already studied. That one is cell potential. It is nothing but E. So this one is with respect to cathode. Then it becomes mine. So here it is simple example for that is galvanic cell. Already I have studied in case of electrochemical cell. So therefore EMF of a cathode, that is standard EMF cathode minus standard EMF of this one. So if you put the values, E naught of copper is nothing but E naught of copper. Copper 2 plus, that is copper in this case. It becomes E naught of this one is equal to E naught of copper 2 plus and copper, then is equal to 0.0591 divided by, it becomes a 2 in this case, log of, and same concentration of oxidized state plus 2, then it becomes copper. Similarly for zinc, it can be written as Zn2 plus can be written as the same factor E naught of Zn2 plus Zn, then 0.0591 divided by 2 log of concentration of Zn2 plus concentration of the Zn. So put these values. This one is equation number 1, equation number 2, equation number 3. So put 2 and 3 in 1, 2 and 3 in 1. So therefore E naught of cell is equal to, right? So first one is about copper, E naught of Cu2 plus Cu1 plus 0.0591 divided by 2 becomes 2 in this case. Then log of copper 2 plus divided by copper minus of E naught of Zn2 plus Zn 0.0591 divided by 2 log of Zn2 plus Zn in this case. For the same equation, so this one is nothing but E naught of cell. It becomes first with respect to copper, this one copper minus of Zn2 plus then the plus of 0.0591 divided by 2, it becomes common, and log of the copper 2 plus, and it becomes Zn divided by Zn2 plus, it becomes common. Okay. So this is nothing but E cell is equal to, this one is E naught of a cell, what you have determined by using that equation, and it becomes plus of 0.0591 divided by 2 log of concentration of Cu2 plus concentration of Zn2 plus. Because the concentration of Zn, concentration of copper is equal to 1 in this case. Right? So therefore this one is for 2 electrodes. You are considering this is simple galvanization, that is zinc, the heat act as anode, this becomes a cathode. So this one is, you can determine cell potential by using this equation, although it is a known equation. So if you know the values, if you put these values in previous equation, you will get these equation, equation number 2 as well as equation. This is with respect to copper, this is with respect to the, if you put 2 and 3 equation number 1, so you will get this equation. So this is after this one, so this one you need to go on subtracting. These are the 2 factors in this case, right? And this one is common factor in this case, in both the equation. This one is common factor 0.05 divided. So this one is log of the same thing. This is quite mathematical equation. Then E cell is equal to E naught of cell 0.05. So here the concentration, these 2 terms, this one as well as this term is considered as concentration of a solids. It should be taken as unity in this case. If it is a pressure, if the concentration is in terms of a gas, it should be expressed in terms of a partial pressure. So for in general, that is in general. So for this equation, the Nernst equation can be, for this equation, or the Nernst equation can be written as, that is E naught of cell, then 0.0591 divided by here, log of concentration of a E, then concentration of a B, So this equation, it is for general reaction like this one. So it has the particular coefficients for this reaction. The equation can be written as. So here the term N and A, this B, C and D, it can be obtained from balanced chemical equation. So if you consider a simple example like this for some of the examples regarding this equation. So first example is, you can take liquid zinc as well as silver. First example is zinc, it will undergo oxidation, it will act as anode, then silver, it acts as a cathode. So for this reaction, the same equation, that next equation can be obtained as, so here zinc will undergo oxidation with the liberation of 2 electrons. Then 2 plus, then it becomes silver is deposited. But in this reaction, 2 electrons are involved, so this should be multiplied with the 2 in this case. So therefore, the same equation can be written as E is equal to E naught of. So this is with respect to copper as well as not a copper. It should be with respect to zinc as well as silver in this case. E naught of percent, then plus of 0.0591 divided by here 2 electron as involved in the reaction. It should be divided by 2 log of, that is concentration of Ag plus, then concentration of, it should be square, and concentration of Zn2 plus in this case. So here it should be multiplied with this equation, it should be multiplied with the 2 because the 2 electrons involved in this reaction. Therefore, the concentration of Ag plus should be raised to the power of 2 in this case. So this one should be as it is because in this case the 2 electrons will be transferred to the Ag in this case. This is a simple example by considering this one. The second example one is, you can consider the more number of electrons, like aluminium, it liberates 2 G electrons, then it becomes, if you take nickel for this one, then it becomes nickel. Equation for this one is the same equation can be written as En. Here it will undergo red oxidation and it becomes nickel. It is in plus 2 state. Then same thing, here E plus, and it becomes nickel in this case. Okay. So, but in this case, it should be multiplied by 3 in this case because if you want to balance this equation, it should be multiplied with the 3 in this case. So it should be like a 2 En and it becomes En. Right? So here 2 becomes 6 electrons are involved in this reaction, 2 into 3. So it becomes, therefore the equation can be written as E naught of 7 then plus of 0.0591 divided by 6 electrons on 3 into 2 in this same thing, 2 into 3 in this case. So therefore log of the same thing. So first one is nickel, it becomes 2 plus, it becomes Q, and it becomes aluminum, it becomes square. Right? So these are the 2 examples. So you can consider n number of reactions, so you can obtain this equation. This is the first example. That one is zinc as well as zinc will act as anode and silver will act as cathode in this case. For this reaction, this is a general reaction by using this which one? Cell in this case. So this one is Nernst equation for this reaction. Similarly, if you can consider more number of electrons, and for this reaction, this aluminum will act as anode and this nickel will act as cathode. So for this reaction, Nernst equation can be written as like this.